And we discussed already in the response. Another question is, how do I take off once the delay is over? You can continue eating, but let's start. So, you know that y prime is going to stay at 0 until the delay is finished. After the delay is finished, how do we take off? Do we take off with continuity in the curve or with a corner, the discontinuity in the slope? So, do we take off like that? Here is, let's say, what I use in your class, no, I didn't use anything. So let's say T0 is the time the step change happened. So until time T0 plus D, you know we are not going to move from 0. Okay? Because the effect takes time to delay before it happens. But at time T0 plus D, how do we take off? One possibility we take off with the discontinuity. Another possibility is we take off without the discontinuity. Okay? So this is the case, corner, no corner. Which is by far the most common case is no corner. So even though the apparent delay often will be bigger than the d that you have in the transfer function, because normally you don't have a corner. When do we have a corner? Actually, this is about the only usage I have ever found of a sister theorem to the final value theorem called the initial value theorem. That says that the limit as time goes to 0 of a function of time is the limit as s goes to infinity of s times the Laplace transform of the function. And using that on the beginning slope, this is no corner beginning slope. At delay, the slope is 0, while with corner, the slope is different than 0. But anyway, I'm not going to ask you for the initial value theorem. I will not put that in the exam. And makes a nice little problem, but we'll skip that for more important.
Wait,
Anyway, but I will ask you to be able to draw if it's a corner or no corner. So using the initial value theorem, I can prove the following. That if and only if the pole excess, and I call pole excess the number of poles minus the number of zeros. So if I have 3 poles and 2 zeros, my pole excess is 1. If I have 4 poles and 1 zero, it's 3. And I always have more poles than zeros. Always transfer function should have denominator of higher degree than numerator. Poles is the denominator roots, zeros are the numerator roots, therefore I always have more poles than zeros. So the pole excess is always at least 1, it cannot be 0. Okay? If it's exactly 1, I will have the corner. If it's 2 or more, no corner. So corner in the response, if and only the pole excess is 1. If it is greater or equal to 2, no corner. So in the previous example that I had done, trying to remember what I put s minus 1, s plus 2, s plus 3, e to the minus 7s. How many poles? 2. How many zeros? Do I have a corner?
yes.
Yes. So I could have said, furthermore, here was 45, here is 50. We're going to minus 5 over 6. With inverse one oscillations, I would first go up with a coordinate. I would see here a coordinate. And then, Josh.
Is a corner, when you draw, it's a straight line? So it's going to be is it a straight
It's a
line?
discontinuity.
So
It means a discontinuity at the time the time delay is full. Okay, let me do, what if I had s minus 1, s plus 2, s plus 3, s plus 4, e to the minus 7. And so what will that be? Same time, let's say 45, here is 50. The new steady state would be different because I have minus 1 over 24. So it would come down to minus 5 over 24 in this case. Because
wouldn't it be 52 this time, since you have a delay of 7 instead of 5?
oh, I meant to put the same delay I had here. I have used 5 before, right? Change it to 5. Thank you. So in this case, I wouldn't see the coordinate 5. It would continue like that, and at some point, I mean, you will see it curve up. So the apparent time delay would be higher than 50 if you try to eyeball something, but when it starts taking. And you wouldn't see ever discontinuity. It would be all smooth curve. Well, here, you see a distinct discontinuity. Okay.
You just kind of do it. This one kind of goes like that, and the other one's kind of straight up like that. I'm just trying to.
It definitely goes up before it comes down since it has an inverse response. If it has a corner, immediately after the time delay, you see the discontinuity. If there's no corner, it curves. There's a curve. If it goes up, it goes like that. If it goes down, it goes like that. But there's no discontinuity. With a corner, it would be this, or it would be this way. That's the difference. Felix.
how come if it's not continuous and it has a corner, the line doesn't break with a space?
Otherwise, it's discontinuity as well. That's what happens. It's mathematics. It's results of mathematics. If you're interested, I can do the initial value proof in my office. Expect about half an hour, but I'll be happy to do it. No, I'll be happy to do it. All right. So that's number 5, correct. Number 6 pertains to, I believe it was Robert who had the very astute observation earlier. Another effect of the zeros is what happens if a zero is very close to a pole. If it's exactly on, they would cancel, but models are not perfect. Cancellation between a pole and a zero should only be happening if we are with negative real part, left-hand side. Because if it's on the positive real part, cancellation of pole and zero, even if it's off by 10 to the minus 10, you have a very different system. The system blows up versus the system being stable. So you never cancel poles and zeros from the right-hand side if you have positive real. But on the negative side, on top of each other, they cancel. What if they are very close? Suppose that I have something like okay, here I have a dominant pole is minus 2, but there's a zero at minus 2.01. Almost on top of each other, not quite. What does that mean? I still have a term e to the minus 2t because of that pole. But having a zero very close to the pole means this pre-exponential factor is going to be tiny. That's what happens. So if you have this really tiny, you are not going to be seeing it. So this is a case where even though the system has true dominant pole -2, it will act as if the dominant pole is -3. You're not going to really be seeing the -2 because the pre-exponential factor in front of it, the -2t, is really tiny. With me? So let me write here, if a left hand side 0 is very close to the pole, the effect of that pole may not be observed. In other words, the system may be as if it didn't have that pole. System behaves as if that pole didn't exist. Okay? And of course, if they're identical, that pre-exponential factor is exactly 0. So it doesn't exist. Clear, guys? One last one. Not only can we draw the picture, how it goes to steady state and all that, we can actually even say how long it takes for our system to reach steady state. At what time our system will reach steady state. So the very last thing I want to put, number 7, is time to reach steady state. I'll write over. Clear so far? We're okay? Any questions on number 6?
The question I would have would be, it's kind of arbitrary about how close they are to one another. So if it was like 2.06, 2.07, 2.08, 2.1.
Well, you can say, remember with the, yeah. Normally you would say it unless, let's say, you have two significant figures close, something like that. I can't give you a really hard number on that, but be aware of that possibility. If you have a pole very close to 0, the effect of that pole may not be seen. The system might behave as if that pole didn't exist and the 0 didn't exist. Okay. Let's now, the last thing I want to discuss, and you can do your homework. Matter of fact, let me pull up the homework, do an example, just with slightly different numbers, just like the part of your homework. Since you only have today and tomorrow to do it, I think it's fair if I give you a lot of help on that. So after I cover that, I will do an example. Just like, I'll just change a couple of numbers. So you have to do it a little bit, essentially doing the part of the homework that you couldn't do. Okay, so the last thing, number 7, is time to steady state.
I can't believe it. That's the last thing.
So of course, the standard steady state only if my system is stable, right? If I have even one pole that doesn't have a negative real part, there is no steady state, there is no time to steady state. Here's another problem I explained. This is step change time. This, of course, the delay. And tau dominant is called the dominant time constant. And it is -1 over the real part of the dominant pole. This stands for real part, and this is the dominant or the rightmost pole. Okay. So let me explain, first of all, let me add something a bit longer in the case of input. Without inverse response is extremely reliable. For inverse response, elongate that. Okay, how do we get that? Well, we know that y prime of t is going to be 0 for time less than, we did that so far with step change at time 0. If we have step change at time t naught, it will be 0 until time t naught plus b. Obviously, it's not going to move before the time of the step change. So it's going to be, and as we will see, maybe today, hopefully today, at times greater than t naught plus d, can you read this as t naught plus d? It will be something e to the minus whole 1 t minus t naught plus d plus something e to the minus p2 t minus t naught plus d, and so on. That's what it will be, the response. So I'll have a response without the delay and the step change happening at time 0 would have been e to the minus p1t. If you have time the step change happened t naught and a delay d, what was 0 is now t naught plus d. Think about what is your time that things happen, when do things change? They change obviously after the step change happened, and they stay unchanged for the time delay. So for time t naught plus d, nothing changed. So y prime will stay at 0 until t naught plus d passes. And then it changes t minus t naught plus d. Okay? Doesn't matter if it's complex or real. If it's real, that's simply minus 1 over p dominant. If it's complex, minus 1 over the real part of the conjugate pair. So I'm going to lost it.